Okay, all right. So today is 25th, which is Tuesday. 25th of April. Now, I'll not say anything about the review from last time because we are kind of uh, tight on schedule. So I'm just gonna go ahead and talk about the things that haven't been talked before. So let's start with signals that are periodic in N. Discrete time signals. We're talking about discrete time signals, by the way. Discrete time means dt. Dt means discrete time. Discrete time signals, periodic in n. Actually in time, but now time is an integer, right? We're not talking about time per se. We're talking about sequence actually. So, so the signal, the discrete time signal xn. When we talk about discrete time signals, the parentheses will be changed to a bracket, a straight bracket, and the variable inside the bracket would be an integer. Okay, it cannot be a real number. It has to be an integer. So this means whenever you see this kind of notation, it means that the x is a discrete time signal. Okay, the discrete time signal, nth sample of the discrete time signal. The discrete time signal xn is periodic in uh, in n if there exists a number, an integer n. Okay, n belongs to an integer. Z, the capital Z there stands for the set of integers. If there exists an integer n such that xn is equal to x n little n plus big N, okay, for all n here. So in other words, periodic signals in n will repeat themselves every big N samples. Okay, so xn will be repeated every big N samples. Okay, the concepts just like the continuous time periodic signals, but now we're talking about discrete time, so you might have to be careful about the variables. So for example, this is a periodic signal in N, discrete time in N. Yeah. So I'm just gonna write down this, this. Okay, I'm gonna write down this, and then this bars, and this, and so on, and then this bar, this bar, and so on. So you see, if you look at this graph, okay, we have 0, 1, 2, 3, 4, 5, 6, 7. -1, -2, -3, -4, -5. The value of the signal is, let's say it's 3. So this signal is x. So you see here that this signal is repeated every 4 samples, right? Here, starting from n equal to 0, it repeats itself at n equal to 4, and it would be repeated at n equal to 8 and n equal to -4. So every 4 samples, you're going to see the same signal over and over again. So this signal is periodic in n with period of 4 samples. So here, this signal is periodic, periodic in n with period equal to, I think I should write it down, move it down here, with period equal to 4 samples. Okay, if you notice here, the unit is samples. It is not seconds. It is not days. It is not hours. It is not minutes. It is samples. Okay, this is the unit of, this is the time unit of discrete time signals. So you may be asking, what is period? The period is the smallest value of n. Okay, it is the smallest positive value of n for which this equation is true. That would be the period. You see, if you look at this signal, you may say that it repeats itself every 8 samples, right? But 8 is not the smallest value. It is 4, which is smaller than 8, right? And you cannot find any number smaller than 4 for which x is repeated. So 4 would be the period of this discrete time signal. So this discrete time signal is periodic in n with period of 4 samples. Okay, so that should not be any very difficult. Now, when we talk about periodic signals, we don't talk about energy, but rather we will be talking about peak power when dealing with periodic signals. Okay, we won't talk about their energy, because the energy of any periodic signal is infinity, and it would be meaningless to talk about energy because it doesn't tell you anything about the strength of the signal, because it's all infinity, right? You cannot compare anything, because since it would be infinity. So to talk about strength of periodic signals, we would talk about energy per unit time. So in this case, because it is discrete time, right? So we would talk about energy per samples per period. So rather, we talk about their power, okay? And the power of a discrete time periodic signal is defined as Px equal to 1 over the period. And 0 means the period. And the summation of the magnitude of xn squared. This means you have to take the magnitude first in case that it is complex value, right? If it is not a complex value, you can just square it, doesn't matter. But if it's a complex valued signal, then you'd have to take only the magnitude, not the phase. You take the magnitude of it and you square it. This is the magnitude squared. And we do this for n samples only. You can start anywhere, but you have to finish every n samples. So you can start anywhere means that n could be any value. Okay, n could be any value, but then there has to be n0 values of this added together. So the end would have to be a plus n0 minus 1. Okay, And if you count the number of samples here, added together, you're going to find that the number of the samples here will be equal to n0. Okay, where n0 is the period. For example, for this signal, right? For the signal above, for example, the signal above, which we know that it is periodic, right? The signal xn above is periodic. Oh, periodic with period equal to 2 samples. So the power of that signal would be 1 over 2, right? And then, because this signal is a real valued signal, you could just square it. So it would 3 squared plus 3 squared plus 0, 0, 4 samples starting from 0. You can start anywhere, but you have to make sure that you have counted the number of the samples you are adding is the periods, okay, the samples in the period. So in this case, it is 3. I'm starting at 0, so it's 3 squared plus 3 squared plus 0 squared plus 0 squared. Okay, so it would be 3 squared plus 3 squared plus 0 squared plus 0 squared. That would be 18. No, that would be 9. 9 units. I'm just saying it is units because we don't know the unit of x, so we can just say it is units. All right, so that is not difficult at all. Okay, now the next one has to be even and odd. Even and odd, I'm just gonna touch on it because you guys have already known it, so it is a waste of time to talk about it in details. Even and odd discrete time signals. So what do I mean? What do we mean by even signals and odd signals? Okay. Even signal means that it is symmetric about n equal to 0. So here, this is an even signal. What about odd? Xn is equal to minus x minus n. Okay, this is odd. Okay, this is easy. So let's just leave it like that. This signal here is neither even nor odd. Okay, this is neither even or odd. All right. Okay, good. You done? Now, let's look at this signal again for one last time. My question for you is, can we do anything to this signal? Can we make a transformation to this signal so that it becomes an even signal? Can we shift right or left so that it becomes an even signal? Can you do that? If I give you this signal and I ask you, can you do a time transformation to this signal so that the result would be an even signal? Can you do that? I mean, is it possible to do that? Is it possible to shift this signal to the left or to the right so that the result becomes an even signal. Is it? So this is clearly not even nor odd, right? It is neither, neither one of them. Can you shift left so that it is even, or can you shift right so that it is even? It turns out that for this one, it is impossible to do that, right? You cannot shift left or right so that the result becomes an even signal. Because if you do that, you'd have to shift. If you want to shift left so that if you want shift it to the left so that it becomes even, then you have to shift it 0.5 samples, right? So it becomes an even signal. But you cannot do that. You cannot shift it 0.5 samples because the number of samples that you shift has to be an integer value because it is a discrete time signal, right? So you cannot just shift it by 0.5 samples. So in this case, it is impossible to make it even by shifting alone. Okay? Okay, so I guess we're done with discrete time signals. In these 2 days, in these 2 lectures, it will be quite fast. So please keep up. Now we will be turning our attention to systems. So discrete time systems. We're done with discrete time signals. So now we'll talk about discrete time systems. Okay, just like when we talked about continuous time systems, we have an input signal, but this time the input is a discrete time signal, right? And we feed the input signal to a system. This system would be called a discrete time system. Okay, discrete time system. And let's name it T. Okay, let's give it a name. The name of this system is T, and it will give you an output signal, which is also discrete time, and let's call the output Yn. Okay, and we will use the notation Yn, which is the output, is T of Xn. So in this notation, the system T is given the input Xn, and the system will process the input Xn. Once it is done with processing, it will give you the output signal Yn. Okay, so this is what the notation means. For example, the system T1, when given the input signal Xn, might give you the output Xn squared. So the system T1, what it does is it will be taking the square of the input signal and it will give you the output, which is the square value of the input, right? Or T2 Xn might be equal to 5 X of n. Okay, or T3 X of n is defined by I'm sorry, Yn equal to T3 of Xn such that Yn minus 1 plus 0.1 Yn is equal to X of n minus 0.2 X of n minus 1. So what the systems T1 and T2 are not difficult to understand, right? It is rather straightforward. But T3 is trickier to understand because T3 is not defined straightforwardly. The way that the system T3 is defined is by means of this difference equation. This type of equation is called the difference equation. It is a discrete time version of differential equations. Okay, if you remember differential equations, right? In differential equations, you have derivatives inside, right? dy by dt is equal to something, right? Or d squared y by dt squared is equal to something. But here, we are replacing the derivative with, or the time shifted version of the discrete time signal. So you may look at this just like dy by dt, okay? And this is going to be dx by dt. So replacing the derivative notation by the difference, the shift in time notation. So this defines the system T3, right? So this is called, this type of equation is called difference equation. I guess what I'm saying is that you can, discrete time systems may be defined in a straightforward manner like this, or they can be defined by means of difference equations like this. So in this case, this system will, the output yn from the system would be the value of the input at time n minus the value of the previous input. This is the value of the previous input, right? Multiplied by 0.5, 0.2, and subtract this to the value of the present input and minus the value of the previous output. So you see what I'm saying? So in this case, it is xn coming in, right? And then you delay it. Delay one sample. Delay one sample. And then you add them. Oh, multiplied by 0.2. Sorry. And then you add them. And then this is yn. And then you'd have to delay one sample. And then, sorry about this. And then you add, subtract. Okay. See, you have an input signal coming in, the discrete time signal, of course. This one is here. Okay, xn is here, this guy. It is waiting right here. And then you have this term, right? This term is 0.2 times the previous value of the input. So what does it mean by previous value? Previous value means that you have to delay it by one sample to get the previous one, right? Delay by one sample. So the signal here is the previous sample, okay, and then multiplied by 0.2. So here, the signal at this path would be 0.2 times x, or at n minus 1, and then you subtract it to xn. Got that? And then you have to move this to the right and subtract it from the rest. I think I have to have 0.1 somewhere, right? I have to have 0.1 somewhere. Sorry, I have to have 0.1 here. Sorry about that. Times 0.1. No, times 10, times 10. times 10. And this would be yn. Yeah, sorry about that. The factor 10 comes from point 1 there. Okay, factor 10 comes from point 1. So this is a block diagram representation for that difference equation. Okay, so what you need to realize is that xn minus 1, this is the delayed version of xn, for just one sample delay. This is previous sample, previous value of the input. Okay. Right. Okay. Now we will be talking about linearity, some important properties of discrete time systems. There are a lot of discrete time. There are infinite number of discrete time systems in the universe, right? But here we are only interested in some of them. The systems that we'll be interested in will be linear systems and time invariant systems only. Okay, we are only interested in linear and time invariant systems. We will not pay attention to any other systems in this course except linear and time invariant systems, discrete time systems. So let's talk about what they are, linear and time invariant discrete time systems. So the first thing is linearity. A discrete time system is linear. A discrete time system T is linear if the output from a linear combination of the input this is the output from a linear combination of the input, right? A linear combination of input signals is equal to the linear combination of the output signals, the same output signals. So if you remember, this is exactly the same definition of linear systems in the continuous version. So the notation here doesn't change at all. The concept doesn't change, but details change. Just the details, just the time. In the continuous time, we had t, right, as the variable, but in the discrete time, the t will change to integer n, which is the sequence number. Okay. So example of linear systems are the usual. Okay, the system defined by yn equal to 5 xn. This is a linear system. Or yn equal to 5xn minus 4 xn minus 1. This is also a linear system. You can prove it actually. And or yn plus yn minus 1. equal to xn. These are all linear systems, linear discrete time linear systems, and so on. Okay, these are all linear systems. Examples of systems that are not linear is yn equal to 5xn plus 2. Okay, the reason why this system is not linear because there is a constant value here added. Whenever you see a constant value here, you can safely say that the system is not linear. Okay, for example, this system is linear if this value is 0. You must not have any value, a constant value added. If you see a constant value, then it is not linear. Okay, or yn equal to absolute xn. This is also not a linear system because there is an absolute value there. Okay, or yn plus x of n minus 1 times y of n minus 1 equal to xn. This is also not a linear system. If you notice here, I'm trying to make each of these systems very similar to the systems at the top. Okay, here, this is a linear system, but as soon as I add 2 to it, it is not linear anymore. See, this is the top one is a linear system, while the bottom one is not. As soon as I'm adding 2, it is not a linear system anymore. This system is linear, right? But as soon as I multiply yn minus 1 by xn minus 1, it becomes not linear anymore. Okay, it is not linear anymore. Okay, so these are examples of nonlinear systems. Okay, all right. Now the next one is time invariance. Just like when we talked about time invariance in continuous time systems, the concept is still the same. But the detail is you have to talk about n samples, not time. So that's just the only difference. Time invariance. Time invariance. Okay. It goes like this. If you still remember, the system T is called time invariant if whenever whenever T of xn is a signal yn, we have T of x n minus n0 equal to y of n minus n0. So what it says is that the property of the system, the characteristic of the system, or the behavior of the system is invariant to shifting in time. Okay, is time invariant. The behavior of the system doesn't change with time. Okay, so the behavior, the way it responds to the input, the behavior, the way the system responds to the input is invariant to time. Okay. Regardless of the time that you apply the input to the system, the response would be expected to be the same. All right? Doesn't matter what time we apply the input, the response would have to be the same. So this is what it means here. So in other words, to check whether T is time invariance, okay, we kind of like, we draw this diagram, right? We have Xn coming in, okay, we put it to the system T, right? And then we delay it by N0 samples. On the other hand, in the lower path, we delay the input by N samples first, and then we put the delayed version to the system T. Now, the signal that comes out in the top would be this would be y. Sorry, this would be T of n, T of xn, and then you replace n with n minus n0. That is the signal that comes out at the top. Now the signal that comes out in the bottom would be T with the input shifted by N0 samples. Okay, and then you compare these two signals. If these two signals are the same, then the system T is time invariant. But if these two signals are not the same, then the system T would not be time invariant. Okay, so Ti, if these are the same signal. Okay, if these two signals are the same. Okay. For example, if I have the system T of x equal to x of minus n, okay, then I'm claiming that this system is not time invariant. This system is linear, but it is not time invariant. You see, when we talk about linearity, we are talking about the value of it. We are not interested in the time information. Okay, we're only interested in the value of it. But when we talk about the time invariant, then we're not interested in the value of it, but we're interested in the time information. Right? When we talk about the time invariant, we are interested in what inside the parentheses, not outside. But when we talk about the linearity, we are not interested in what inside, but we're interested in what outside. So I hope you're not confused. Now, so I'm gonna prove. I'm gonna show you that this system is not time invariant. So let's look at these signals. Let's look at the upper path. You see, uh, 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 now T of x n, and then plug in, replacing n with n minus n0 would be x of minus n minus n0, okay, and that would give you x of minus n plus n0. Now, as for the lower path, T of x n minus n0 Okay, this is just x of minus n0. And so you see, these two are not the same, right? These are not the same. So the system is not time invariant. Now you may have a question in the lower equation. Why is this negative? Why is this negative and why this is not negative? Why the negativity only applies to n but not n0? That's because the way the system behaves, okay, what the system does is that it will be putting a negative sign in front of n only. This is the time. So you see the time here, the time information is only in n, but not n0. N0 is just a constant. So what it does is that it is gonna kind of like horizontally flip the signal left to right and right to left without even caring about n0. So that's why we have only the negative symbol in front of n, not n0. So you see they are not equal. So this system is not time invariant. Okay. Yeah, I'm gonna show you. Uh, no, let's not wasting time. I think you all understand here. So I'm not gonna talk around it anymore. It's not difficult. You may want to plug in x equal to un, right, to see what happens. If you plug in, you may see this clearly, more clearly, if you let xn equal to un, okay, and draw graphs of tun and then plug in n equal and then shift it. This is the shifted version of tun, right? This is the shifted version, and t of un minus n0. Okay, and compare them. All right. Now we are in a position to talk about discrete time linear time invariant systems. A discrete time system, a discrete time system is linear time invariant if it is both linear and time invariant. Okay, it possesses the properties of linear and time invariant at the same time, right? When that is true, then we call the system linear time invariant. Example. So let's suppose that the system T is a linear time invariant system. Okay, when we talk about linear time invariant, I'm just writing down LTI to save time. I'm too lazy to write down linear time invariant, so we're just writing down LTI. So let T be an LTI system, and suppose that the way it responds to the unit sample signal, the output of the system T, if the input is delta n, So this means that the response, its response to the unit sample signal is UN. Okay, whenever you give it a unit sample impulse to the signal, to the system, it will give you the unit step signal out. The question is, we want to find the response from the system when the input is the unit step signal. Okay, first you have to understand what is going on here. There are three pieces of information in this example. The first information is T being a linear time invariant system. So whenever you see this sentence, you have to know that two conditions apply. The first condition is that the output of a linear combination of the inputs would be the same linear combination of the outputs. The second being that T is time invariant, means that it doesn't matter when we apply the input, the output would still be the same. Okay, so that is the first sentence. Second sentence means that the question tells you that whenever the input is a unit sample, you're giving the unit sample to the system, then the output of the system, it will respond with the unit step signal. Okay, nothing else. It doesn't tell you anything else other than unit sample. Now, the third information, which is the question itself, is that it asks you to find the response to this system when the input is the unit step. You have to be aware that this input and this input are not the same. So don't expect the response to be UN. It will not be the same UN there because the inputs are not the same. Okay, so our task is to find what is this guy. Now, you have to solve this example, you have to use the properties of linear time invariance, obviously. Okay? So, first, we start with figure out how to write down. We have to figure out, to be able to use the linear time invariant properties, we have to figure out how to write UN as a function of delta. If you cannot find the relation between U and delta, then you will not be able to solve this one. So you have to think for a while, what is their relation, U and delta? If you plot the graph of U, okay, if you plot the graph of U, you see that the graph of U will be here, right? And so on, and then 0 and 0 when n is negative. So this is UN, right? This is UN. 0, 1, 2, 3, 4, minus 1, minus 2. Now, when you look at the leftmost sample, this is delta, right? This is delta. If you, yeah, delta is one sample only, right? And that is at n equal to 0. So this is delta. So what is this at? This is delta shifted to the right one sample. So this is delta of n minus 1. And this is delta of n minus 2. This is delta of n minus 4, and so on. Okay? So once we realize that, let me write this down. This is delta n, right? This is delta n minus 1. This is delta n minus 2. This is delta n minus 3, and so on. So UN is just the summation of all these deltas, right? You add these deltas together and you're going to get UN. So we see that UN is delta n plus delta n minus 1 plus delta n minus 2 and so on. Okay, and then we write it in the summation notation, in the sigma notation, and that has to be k starting from 0 to infinity, right? When k is an integer and delta of n minus k. So this is un, right? This is un. So once we know their relationships, okay, then we can apply un. We can apply this infinite sum as the input to t. So we are replacing u here with this infinite sum. So, yeah, so what we are asked to find is t of u, right? T of u would be t of delta, I'm sorry, t of sigma, starting from k equal to 0 to infinity delta n minus k. Yeah. Okay, and now we see that the input is a linear combination of deltas, okay, placed at particular samples. So we can use the linear property of t, right, to bring t inside of the summation. We can bring t, we can interchange t and summation using the linear property of t. So I can bring t inside of the parentheses to get summation k equal to 0 to infinity t of delta n minus k using linearity. Okay, by the assumption of the problem, because the system t is linear time invariant, right? Means that it is linear as well as time invariant. So I'm using linearity here to bring t inside. And then, as for, you have to figure out what this is. Okay, what this is. So this is just the output of the system when we shift the input delta k samples. But we know that system t is invariant to shifting, right? Because it is time invariant. So this is just the output of t when the input is delta and shift k samples. Okay? So this from the ti property, right, is just equal to t of delta n, right? And then replace n with n minus k, right? Okay, by the ti property. And we know that t of delta is what given in the question, it is u, right? So it is un. And then you replace n with n minus k. So this is equal to u of n minus k. Okay, so this is u of n minus k. Right? So I'm plugging this u of n minus k to the summation there, and I'm gonna get equal to summation where k goes from 0 to infinity of u of n minus k. Okay, are you with me? If you're not with me, please let me know. Okay, and then I have to figure out what this is, right? I have to figure out what this is. So what should we do to find out what this is? I guess to find out what this is, yeah. Now, so what is this? So let me write it down. This is just, okay, when k is 0, you have un, right? When k is 1, we have un minus 1. When k is 2, you have un minus 2. When k is 3, you have un minus 3, and so on. So what is this? Can you tell me what it is? So what is UN? UN is 1, 1, 1, 1, 1, right? 1, 1. This is UN. This is UN, right? Starting from n equal to 0. Here, n equal to 1, n equal to 2, 3, 4, 5, 6. So what is UN minus 1? Let's use UN minus 1 is 0 here. Okay, but starts from 1, right? This is UN minus 1. So what is UN minus 2? UN minus 2 starts at n equal to 2, right? So here. This is UN minus 2. So what is UN minus 3? It starts at 3. UN minus 3. And so on. But now we have to add them together, right? Here, this says that we have to add them together. So we have to add these ones together. And if you do that, if you add them together, okay, you add them together. Add them together, what you have here, at n equal to 0, you're going to have 0. The big 0 coming out, right? Make it big, 0. At n equal to 1, you're going to have 1, right? At n equal to 2, you're going to have 2. At n equal to 3, you're going to have 3, 4, 5, 6, and so on. Okay? So what kind of signal is this? It starts, oh, no, sorry. I think, excuse, yeah, I think this is 1, this is 2, 3, 4, 5, is 6, is 7, and so on here. So what kind of signal is this? Of course, when n is negative, it is 0, right? When n is negative. Okay. So first, we know that it starts at time 0. It starts at n equal to 0. Second, at n, the value of this signal is n plus 1. Right? For example, here, at n equal to 4, the value of it is 5. At n equal to 5, the value is 6. So at any arbitrary n, the value of it is n plus 1, and it starts at n equal to 0 as well. So we know right away that what TUN, right? TUN is equal to n plus 1, right? And then times UN. That is the answer. Okay? You can plug in, see for yourself. When n is negative, u is 0, so you have all the zeros out of 0. But when it's 0, when n is 0, u is 1, right? And then you have 1. Okay, when plug in n equal to 0, you have 1 here. N equal to 2, u is 1. N equal to 1, u is 1, and then 1 plus 1 is 2, so you have 2 there, and so on. So this is the answer. Okay, so to arrive at this solution, you have to use two properties. First, you have to use the linearity, and second, you have to use the time invariance property. Any any question, please? No. It's just like integration. Okay, summation is like integration. Next one, Bible stability. We've seen Bible stability before, right? But then it was about continuous time systems. But now we're talking about Bible stabilities of discrete time, linear time invariant systems. The concept's just the same, but the details different. Okay. Uh, Discrete time LTI system a discrete time actually let's leave linear time invariant for a while. Let's talk about just discrete time system. Sorry about that. A discrete time system T is bounded input, bounded output, bounded input, bounded output, bounded output, stable. So this is too long, right? This is very long, such a long words. So we call it Bible for short. Okay, Bible for convenience. The discrete time system T is Bible stable if and only if whenever the input is bounded, the output is also bounded. So whenever the input is bounded, the output is also bounded. Okay, so what do I mean by bounded input? Input is bounded means that the magnitude of the input is less than some value for all n. Okay, there is an upper bound for the input. Okay, there is an upper bound. You can find an upper bound for the value of the inputs. If you cannot find an upper bound, then it is not bounded. It is bounded if you can find such an upper bound. Also, the output is bounded means that you can also find another upper bound for the output. Okay, so whenever there is an upper bound, whenever there is an upper bound for the input, there is also an upper bound for the output. Whenever that is true, then the system is called Bible stable, right? And these conditions will be a lot easier when we talk about linear time invariant systems, as you shall see. You cannot have to, you don't have to prove this because proving this is rather tricky. But once the system is linear time invariant, then this condition will be equivalent to something else, which is proven quite easier, okay, more easily. So let's leave it for now, and we will see it again when we talk about linear time invariant systems. The next is causality. Uh, a discrete time a discrete time system is causal if the response to the present input doesn't depend on the values of the future inputs. Okay, a discrete time system T is causal if the value of the present output yn does not depend on the values of the future input. Xn future input means xn plus 1, xn plus 2, and so on. So in other words, yn does not depend on xn plus 1 or xn plus 2 or xn plus 3 and so on. It can depend on xn, it can depend on xn minus 1, it can depend on the past values of the input, but not the future values. So when that is true, the system is called causal. All right, for example, yn equal to xn minus xn minus 3. This system is causal. Okay, this system is causal. But this system is not. This is not causal. The reason why it's not causal is because it depends on the future. This is the future value of the input, right? It is 3 samples ahead of the future. So it is not causal because the present value of the output depends on the future value of the input. Right? So this is not causal. But in the first system, the present value of the input depends on the past value of the present value of the output depends on the past value of the input. So the first system is causal. Even though it depends on the past, it doesn't depend on the future. So yeah, it is causal. Okay? Okay. Alright, so that is the end of chapter 7. So let's go ahead and talk about chapter 8, which should be the last chapter we'll be talking about in this course, and last chapter number 8. In this chapter, we'll be focusing only on linear time invariant aspect of the system. Okay, we are only considering systems that are linear time invariant only. We're not talking about any other systems. Okay, so this chapter is called discrete time, linear time invariant systems. Okay, we're focusing only on discrete time systems that are linear time invariant. Okay. Now, if you recall, when we talked about linear time invariant continuous time systems, the way we deal with those systems was we defined something called impulse response, the impulse response. Now, the same idea applies to discrete time linear time invariant systems as well. So we're going to define something called the impulse response of a discrete time linear time invariant systems. So we will use the concept of the impulse response to analyze discrete time LTI systems, just as we did in chapter 2. In chapter 2, when we studied continuous time LTI systems. Right, so we're gonna use the concept of impulse response, but now in this chapter it has to be discrete time, okay, not continuous time. So what is impulse response here? Recall, the impulse response is the response, the output from the system, but now in this case it has to be discrete time, linear time invariant. Okay, and let's call the system T, right? Now we're applying, instead of having any arbitrary input, okay, the impulse response is defined as the output when the input is the unit sample. Okay. Notice here, I'm not calling this unit impulse, I'm calling this unit sample because it is discrete time version. So whenever it is a discrete time, we call it this unit sample, not unit impulse. Now, when we apply the unit sample to the discrete time linear time invariant system T, the output will be called the impulse response. Okay, discrete time impulse response, and we use the notation h of n. Okay, but we have to have one additional condition, and that is the system T has to have 0 initial conditions. Okay, no initial conditions. Okay, the way that the impulse response is defined is, first you have to have the input as the unit sample. Second, the system must not have initial conditions. Whenever these two conditions are satisfied, then the output will be called the impulse response. So, in other words, Hn is defined as T of delta n when there are no initial conditions present. Okay, right. Now, in the continuous time system, LTI system, when we were in chapter 2, if we know the impulse response, we can find the zero state output by performing a convolution integral on the impulse response and the input, right? Same concept goes here. So once given is a discrete time LTI system with impulse response Hn, we can, this is big, right? This is a big theorem. We can find the zero state response of the system to the input Xn, okay, by using convolution sum, the convolution sum. In chapter 2, the name was convolution integral. Okay, in chapter 2, the name was convolution integral, but here the name is changed to convolution sum. In the integral changed to sum because integral was defined for continuous time, and sum was defined for discrete time. And the zero state output y is h of n, sorry, x of n, sorry, h of n, h of n and star x of n. So as we have seen in chapter 2, the same notation is used here. Star means convolution. Okay, so whenever you see this, it is either convolution sum or convolution integral depending on the signals. Whether it is t or n. When it's n, it is convolution sum, but when it is t, it is convolution integral. Now, if you recall from chapter 2, right? If you recall from chapter 2, when we do this is from chapter 2. Sorry, I have to move this a little bit to the left to give some space. When I perform convolution integral between ht and xt, I hope you can recall, the way we do it is we integrating h of tau, right? And then x of t minus tau with respect to tau. This is the way we perform convolution integral. But here, when we perform convolution sum, we are going to change the integral notation to summation notation. Okay, and we're going to drop this d tau because for integer, this doesn't make sense anymore. We don't have d tau anymore. And we're going to change tau to something else, and we're going to change t to n. So, notice the similarity here. We're going to have, by replacing integral notation to summation, this summation goes from minus infinity to infinity, okay, to resemble these, right, the ranges, the lower and upper boundaries, minus infinity to infinity. And then h of tau, you see the integral is with respect to tau, right? The integral is with respect to tau, so tau here is k. The summation here is with respect, the summation here is with respect to k. So integral is with respect to tau, summation is with respect to k. So h tau has to be changed to h of k. Okay, so this is h of k. H of k. And then x is repeated here. Okay, inside of x, t is n, right? T is n. So let's just write down n to reflect this. So n minus and tau change to k. So k here. And this is the definition of convolution sum. You see? Yeah. Question? No? So you see the similarities between this. Again, integration replaced with summation. The integration here is with respect to tau, so the summation here is with respect to k, tau and k, right? And then h tau changed to hk here, and t is actually n, right? Discrete times, so t changed to n and tau to k, and then we have to drop d tau because it doesn't make sense anymore when you talk about discrete times. So this is the definition of convolution sum. Okay. Convolution sum. We're going to use this definition to find the zero state response of a linear time invariant system to any input x. Convolution sum between hn and xn. Okay, and I'm going to ask you for 3 more minutes to talk about basic properties of convolution sums, and very useful properties actually. Basic and useful properties. These properties are exactly the same as the properties of convolution integrals, but so I'm just going to repeat it here without any proof. of convolution sums. Oh, by the way, do you know what it is when I say zero state response? Zero state response means the output of the system when there are no initial conditions at all. Just the response only to the input, but not the initial conditions. Okay, that's what I mean by zero state response. So basic and useful properties of convolution sums. These properties are exactly the same as convolution integrals, namely, first, the convolution sum is commutative. Commutative means you can write Hn star x or you can write x star Hn. They are the same. Okay. So this means that h of n, you can start with h or you can start with x and they are the same. It may seem silly to talk about whether these are the same, but actually it is not that simple. To prove this, it is not that simple because you see, if you look closely, the left-hand side is summation k equal to minus infinity to infinity x of k times x of n minus k, right? This is the left-hand side, but the right-hand side is this. Okay, this property says that these two summations are the same. The results from the two summations here are the same. Well, the equation here looks very naive, right? It looks silly, but if you look closely to the second equation, it is not silly at all. It is not straightforward to prove actually, but I'm gonna leave it. Okay. That was the first property. The second property is associativity. Associative. Says that xn star h1 star h2 is equal to xn star h1 and then star h2. Okay. In other words, because convolution sum is a binary operation. Okay, the word binary operation means that it takes two inputs to perform convolution sums. But if you have three functions to perform convolution sums, you have to do it two at a time, right? Associative property means that you can pick any two. Okay, the order of the two that you pick is irrelevant. Doesn't make any difference. You can pick these two to perform convolution sum first, and then you perform convolution sum between the result from this with x, or you can do these two first and then do the last one, right? So the order of this is irrelevant. That's what's called associative. And actually, the proof of associativity is not straightforward. It's not easy, actually. It is rather more difficult than the proof of commutative. The third property is the distributive property. Bear with me, I'm about done. Distributive property is probably the most useful property that you have to know. Xn convolved with h1 plus, well, actually here, alpha h1 plus beta H1. Okay, basically what it says is that you can look at star as a multiplication operator. You can, so in other words, you can bring the star inside of the parentheses. You can pull it inside of the parentheses, just like you do when you're dealing with multiplication. So when you bring the star inside, you're gonna have alpha x n star h1n plus beta xn star h2n. Okay, so this is the distributive property. See, I brought, what I did was I brought star xn star inside. I take it inside of the parentheses. Okay, but when I take it inside, I have to do xn with h1 here and with h2 there. Well, I have to change it to h2. Sorry, that's a typo. This has to be x2 h2. Okay. All right. I think. Sorry for the delay. I think I should stop now. And once again, the homework problems for Fourier transform has been posted. Please check it out. And I'm gonna post the homework problems for discrete time signals and systems later. Please stay tuned. So, any questions, please? No. And check attendance. I have activated the link already, and the magic letter today is below. Right? Check attendance. And if you don't have any more, if no further questions, I'll see you on Thursday, which is supposed to be the last lecture of this course. Okay, before we take an exam next week on Wednesday. All right, and have a good day. Bye bye. Stop recording.